Okay, in this video we're going to take a look at Coulomb's law. Now, Coulomb's law, by the way we've defined law, is not actually a law. It's a law in as much as it precisely and 100% of the time is going to describe the force interaction between two charges. But Coulomb's law is not that universal law that we're using to describe laws in my class. So what I mean by that is that you do not use Coulomb's law by itself to analyze general interactions. So, for example, if you're going to be studying a general interaction between two charges and you want to use the force perspective, then you use Newton's second law to diagram the forces and explain that interaction. As a part of Newton's second law, the electric force will be redefined using Coulomb's law. So in that sense, Coulomb's law is only a definition. And it's a definition which is going to predict the force interaction between 2 point particles. The one caveat to this is that the charges should not be moving. And I do want to emphasize we're talking about point particles with Coulomb's law. You would not be able to apply Coulomb's law to something like a charged cookie sheet or a tabletop or whatever other shape that you can think of. Even a charged balloon, it would be a close approximation, but it wouldn't be quite right. The one exception to that is that Coulomb's law would also apply to spheres. And it has to do with the geometry of a sphere. So we could be using spheres as long as they're sufficiently separated. All right, now Coulomb's law, as you'll recall, is going to be the electric force is equal to K times Q1 times Q2 over R squared. And I've placed an absolute value sign around F. And I'm also going to place absolute value signs around Q1 and Q2. All right, so let's look at F. This is going to be measured in newtons. All right, K is Coulomb's constant, and K has a value of 8.99 times 10 to the 9th, and that will be Newton meters squared per Coulomb squared. Q1 and Q2, those are going to be measured in coulombs. Common units are going to be nanocoulombs, which is times 10 to the minus 9, microcoulombs, which is times 10 to the minus 6. But you're going to have to convert these to coulombs. And then R is measured in meters, and it's that straight line distance between the two charges. K is further defined by 1 over 4 pi epsilon naught. And this is an important representation of K, Coulomb's constant, whenever we get into capacitors. And so this epsilon naught thing is actually important to us. It saves us some effort, and it kind of shows up in our definitions. So we'll talk about that more a little bit later. But in the meantime, what the heck is epsilon naught? Well, epsilon naught is called the permittivity of free space. And basically all that means is how well an electric field can travel through space. Okay, now this epsilon naught is specifically in reference to a vacuum. All right, specifically in reference to a vacuum. If you're traveling, or if the electric field has to go through some other type of material, then we no longer refer to it as epsilon naught, we refer to it as epsilon, and epsilon is equal to kappa epsilon naught. Now this is going to be something that we work on a little bit later, but kappa is a Greek letter. It looks kind of like a K, but the difference between kappa and K is that K is written with a straight back, and kappa, it's a little more curved. So pay special attention whenever you're writing out kappa by hand, because it may not be obvious that it's a kappa and you might mistake it as a K. So, but kappa is called the dielectric constant. And we'll talk about that more later. You should remember some of this from last year. But it's the dielectric constant, and of course epsilon naught we just talked about. So if you're going to be going through some other material, then you're no longer going to be using epsilon naught, you'll just be using epsilon, and that's because the electric field becomes diminished as it travels through that other material. One of the important ideas related to using Coulomb's law is the principle of superposition. And superposition is basically going to be the net force, or could be the net field when we talk about fields, but it's going to be the net force is just the vector sum of each of the individual interactions. And what I mean by that is this. If we've got three charges, we have charge 1, charge 2, and we'll put charge 3 up here. Now, if we want to know what the net force on charge 3 is, so we want to know what is F net on 3, then what we're going to have is the force of 1 on 3 plus the force of 2 on 3. And these are all vectors. Now anytime you see this vector symbol above your variable, that means you may end up having to go into x and y coordinates. Now if we further assume, just for simplicity, that each of these charges is positive, then that means that the force due to 1 is going to be pointing in that direction, and the force due to 2 is going to be pointing in that direction. So this is the force of 1 on 3, and this is the force of 2 on 3. Now we're not looking at the interaction on 1 or 2. We're looking at how 1 and 2 interact on 3. And I think it becomes pretty clear that we have a horizontal and a vertical component to each of those forces. And so in order to get the interaction, we would have to say F net x is equal to F13x plus F23x. And then we do the same thing in the y dimension. F net y is equal to F13y plus F23y. And then you get into sines and cosines, and so I'm not going to fill this out completely, but we'll get examples of this later. But we have the force of 1 on 3, that's just going to be Coulomb's law. So that becomes KQ1 Q3 over R13 squared. And to get the x component, if we assume that this is our angle theta here, then it becomes cosine of theta. And then we, in the y dimension, plus, right? And then we go to the y dimension, we have F net y, and we get KQ1 Q3 over R13 squared sine of theta. All right, so this is all stuff that you've seen before, but that's the principle of superposition.